Okay, so here we go. Oh, that would be more interesting if I shared my screen, huh? Hello, YouTube people, and from a pitch black screen. Okay, that's better. All right, so sorry about that. I had a little trouble with Google Docs this morning, so because I was spaced out. Anyway, whatever. Um, so where were we? Yeah, so the reading for today is 15.3 and 15.4. As we can see, we're going to talk about the degree, essentially things about the degree of a field extension. And for Monday, we're doing 15.6. I guess we will. I think we're going to skip the ruler and compass constructions because those are fun, but they're sort of but they're actually something you're likely to have seen for those of you who have seen this before. And so I thought it'd be more interesting to go hit some new territory for those of you who haven't. And oh, so yeah, right. So I said, what do I say here? I said problem set 7 is due Monday, March 23, but I think it will be. I should say that it will be fine. So yeah, so Wednesday, March 25th is fine. Yeah, I think Monday is a reasonable target date because we'll have our sort of a problem session again on Friday, and at least we'll give that a shot again. I think we're going to be as I'm already pretty flexible about deadlines, I would say, and and certainly now with all the madness that's going on, I think I'm definitely not going to be fussy about deadlines. So get it in when you can. And I guess I should. Yeah. So, and then I think next week I'll sort of have some better idea of what to do about exam 2. Probably what we're going to do is we'll do it as a take home, and I'll sort of pass it out on Wednesday, March 25th, and then you'll have take whatever time you need to get it done, and on your honor, please don't cheat, but take whatever time you need to get it done. Does that sound like a reasonable plan for exam 2? Say yes in the chat. Yes. Though I guess who's gonna say no because with the teacher asking them because okay, so drop me an email. If that doesn't seem like a reasonable plan, we'll figure something out. Anyway, okay, let's get on to where let's get on to some math. And again, sorry I started a little late there. And thank you, Apurva, by the way, again for picking our sort of play-in songs, which covered my sort of running upstairs and transferring a file from one computer to another. Like right now we have 3 people in my house, me, my wife, and my daughter, and we have at least 9 computers. It's ridiculous, and we're somehow using all of them. It's amazing. Anyway, I mean, they're not expensive computers, but there's a lot of computers in the world these days. Okay. Anyway, so let's talk about the degree of a field extension. So the first thing, just remember this notation over here. Let me remind you. So what does this notation say? This notation says that, remember that K is an extension of a field extension of F. So for K over F, K field extension of F, K is an F vector space because because you can add K elements of K together and you can scalar multiply them by F and they satisfy all the usual rules. So that makes K into an F vector space. That's a strange but very important idea that actually took me personally a long time to absorb. That a field extension is a vector space over the smaller field. In any case, since K is an F vector space, it has some kind of dimension over F, and so we define the degree K colon F to be the dimension of K as an F vector space, and to say that the K over F, or that K, the extension K of F is a finite extension, means that the degree K colon F is finite. Okay, so I guess, so let's look at some small examples of what that phenomenon looks like. So first of all, we'll start with degree 1. What does it mean to be a field extension of degree 1? Well, the fact is that k over f has degree 1 exactly when f is equal to as f is equal to k. So let's see if I can prove that. And then similarly, we'll see that alpha has degree 1 over f if and only if alpha is an element of f. Okay, so I think this will be mostly a review of what all these things mean. Okay, so let's try this. So yeah, let's start. So let's try to do a proof here. Okay, so what does it mean to say that k is a field extension of f of degree 1? That means that the degree of k over f is 1. Well, what does that mean? That means exactly that k has an f basis with one element in it. Let's see if I can make this window bigger. Yeah, basis with one element in it, which means that actually let me make a little space here instead of So what does that mean to say that well, actually let me put it this way. So that means that k has dimension 1 as a vector space over f. All right, see if I can oh, that's not quite enough space. Let me look at a little tiny arrow here. All right, so yeah, so what does that mean? Well, there we go. That means that any non-zero, so when you have a one-dimensional vector space, that means that any non-zero vector will be a basis for k over f. So in particular, the set containing the vector 1, right, 1. What do we mean by 1? So because k is a field, f is also a field, that means they both contain the common element, and f is a subfield of k, that means they contain the common element 1, which is not equal to 0. And so that set containing 1 is a basis is an f basis for k, which means that didn't do that. Oh, there we go. Which means that k is equal to f, because k is equal to exactly all of the f scalar multiples of that basis element 1, which is exactly f. All right. So a field extension has degree 1 exactly when it is the trivial field extension. It's the field extension that doesn't really extend anything. It's just the base field itself. Something like that. Okay, so I was at the same time both trying a sort of new method of writing stuff down and also explaining that. So how is that? Extension of degree 1 means that f is equal to k. Is that okay? Oh yeah. Yeah, so Ravi asked, why does the f basis have to be 1? It doesn't have to be 1, but but I guess I should be a little more precise about what I'm saying there. That 1 is one example of. Yeah, so the statement is really that that the set containing 1 is one particular f basis for k. It's not some sort of canonical f basis for k. It's not the only f basis for k, but it is an f basis for k. So yeah, so I could have picked anything else, and it's just a little more clear that k is equal to f if I pick my f basis for k to be the element 1. So does that make sense, Ravi? Yeah, it's just slightly clearer, I hope. Okay, so so let's try let's try the second part. Alpha. So alpha. Let me. Pardon me for lapsing to LaTeX because it's a little easier to read, I think, than to write than having to write an alpha out by hand. So alpha has degree 1 over f. So yeah, let's start there. So does anyone remember? You can either type in the chat box or write it out. In terms of or just open up your mic and say what it is. Does anyone remember what it means for alpha to have degree 1 over f? Should I remind everyone what the degree over f is?
Yes.
Okay. Good. So good responsiveness. Right. So that's what's going to happen. That alpha is in f. That's the effect of that. But let me remind you the definition. So let me remind you over here in green what the degree of an element is. Degree. That's a weird looking green. Oh well. Of an element over f. Let's say an element alpha over f is the degree of the irreducible polynomial of alpha in f bracket x. Did I type that correctly? Nope. Almost. Right. So the degree of an element alpha over f is or in other words, i.e. So here's some review in this sickly looking green. The irreducible f of x in f bracket x such that f of alpha equals 0. So remember, one of the things we discussed last time is that for any element of a field extension, there is a unique any algebraic element of a field extension. There's a unique irreducible monic f of x such that f of that element is equal to 0. So does that sound vaguely familiar again? Everybody okay with that review? Yes? No? Maybe so? Okay. So to say that alpha has degree 1 over f means that the irreducible polynomial of alpha is going to be of the form is degree 1 or has degree 1. So it must be the form x minus a, where a is in f. Oops. A little bit bigger. Where a is in f. All right. So yeah. So how is it possible that a polynomial can be of the form x minus a, where a is an f, and yet have alpha as a root? Well, the only way that can happen is the irreducible polynomial of alpha is precisely x minus alpha, or alpha is an f. And so indeed, alpha is an f. All right, so that was good. So that was a good review of the degree of an element. Yes, I know it. So as I mentioned, as I mentioned last time, we now have this confusing state where we've introduced the degree of a field extension and we've also introduced the degree of an element, and which seems a little bit confusing, but as one might hope, we'll see in a minute that they're actually in any case that matters, they're the same thing. Okay, so we good with that? We good with the understanding of extensions of degree 1? By the way, who wants to be the next DJ? So Purva was nice enough to willing to be voluntold. Anybody want to volunteer to be the DJ for Monday? Oh, here we go. So alpha has degree greater than 1 means that you have an extension field of F, but it's not an F. That is correct. Right. So yeah. So an element of degree greater than 1 cannot be. An element has degree greater than 1. Yeah. The contrapositive of the second statement is that an element has degree greater than 1 exactly when it is not an F. Oh, hey, Ravi, can you remind me to answer your question that you're asking over Piazza if we get a few minutes at the end? All right. Thanks, Ravi. Okay, so let me move on to degree 2. Well, okay, I mean, you could sort of imagine how to do like a countable set of introductions like this, but okay, we're going to stop at 2 because actually things get more complicated after degree 2. Anyway, so suppose F has degree 2. Sorry, so suppose the characteristic of F is not 2, because and the sort of short answer as to why this works is because well, the reason why we're interested in this is so that the quadratic formula works. Why is this? How do I get this thing to go away? Why did that happen? Sometimes this keyboard thing shows up and sometimes it doesn't. It's very strange. So quadratic formula works. All right. Yeah. So we're assuming that the characteristic of F is not 2, which means that the quadratic formula works. And so then the theorem says if you have a field extension of degree 2, that is, K is an extension of F, and K has dimension 2 over F, then K is a quadratic extension. It's equal to F of delta, where delta squared is the square root of some element of F. And conversely, if delta squared is an element of F, but delta itself is not an F, then the degree of F of delta over F is 2. All right, so let me just do the. I think maybe let's see how we're doing for time. I'll just do part 1, statement 1. Well, let's just prove statement 1 because statement 2 is not so bad. Statement 1. So to say that the degree of K over F. Ooh, I don't quite really care for the sickly green. Let's go back to our royal blue kind of deal. So if the degree of K over F equals 2, means that well, for example, that any two linearly independent vectors, any two elements of K that are linearly independent over F are a basis for K. Well, as Ravi was just saying, thank you, Ravi. That's an excellent prompt. Since the degree of K of F over F is greater than 1, there exists some some delta, sorry, we should start with alpha, some alpha in K such that alpha is not an F multiple of 1. So that means the set 1 comma alpha is linearly independent, and therefore an F basis for K. Right. So yeah. So there we go. On the other hand, but 1 comma alpha squared is linearly dependent over F. So we must have, after dividing, we must have some, actually, let me see if I can go to pen here. We must have A alpha squared plus B alpha plus C times 1 equals 0, with A, and we can't have A equals 0 because then we'd have a linear dependency between alpha and 1, which means that we have some alpha, called C sub B sub 0, C sub 0, which means that we have alpha squared plus B alpha plus C equals 0 for some, oops, there's that green again. Why is that? I want to go away. Okay, there we go. Start that over. No. So turn it to blue, and then, all right, I'll get the hang of this yet. For some B and C and F. Right. So actually, this is sort of a useful, this is I want to point this out. This is a useful technique. I think this is actually in your homework somewhere. It's a useful technique to that when you think about an extension field as a vector space over the sort of smaller field, what you always see is that linear dependencies end up being the same thing as algebraic relations. So this is a very useful technique that comes in handy for a bunch of problems. Yeah, in fact, I think including something on the homework. Where whenever there's just a sort of fun thing that shows up over and over again, that whenever you can find a linear dependency, that's going to give you some sort of algebraic relation like this, or I guess to be more precise, an F linear dependency gives you an algebraic relation with coefficients in F. It's not really. Yeah, every F linear dependency is the same thing as an F algebraic relation. All right, anyway, so the point is that's true. And then to make a long story short, the quadratic formula then gives that, alpha, how does this go again? Alpha equals minus B plus or minus the square root of B squared minus 4AC, which is just 4C here, all over 2A over 2. And there the over 2, that's where we use the characteristics not equal to 2. So which means after a little bit of sort of relatively straightforward algebra, that means K is equal to F of delta, where delta equals the square root of B squared minus 4C. Yep, quadratic. Is that readable? Is that readable written out in LaTeX, or should I write it? I guess I have a little space here, so and a little time, and so should I write that out in terms of as a formula? Actually, let's all vote. Uh, uh, who thinks the words are more readable because my handwriting is terrible, or who thinks the formula would be more readable because it's weird to sort of try to read out a formula? Okay, just say if you prefer handwritten or typewritten for that. Actually, I'll just go while I'm just doing this. I'll just while I'm taking this, just go ahead and type that in the chat box while you're making up your mind. Let me just write it out and see how that goes. B squared minus 4c all over 2. So if delta equals the square root of b squared minus 4c, then k equal to f adjoint delta. Okay, the handwritten is better there. Okay. All right. So anything beyond anything. I've been doing LaTeX for what, like 25 years now, so maybe 30. So I got used to it, but okay, that is more readable. All right, so lesson learned. All right, anyway, so and that's the first implication, and I'm not going to worry about step 1 because statement number 2 because it's not so bad. So are there any questions about the proof of 1? Is that okay? Yes, handwritten is better there. So we good? Yes. How's everybody doing with shelter in place? Y'all doing a lot of cooking? Anybody cook anything interesting? Apurva, what did you make that's interesting? Carlos, what did you make that's interesting? Anybody want to volunteer something interesting they made? Among Ru, you gotta learn how to cook. Now is an excellent time to learn how to cook. You've been living off top ramen, and which is not so easy to find, I guess, actually. Oh, chili verde, fantastic, awesome. Yes, we make that sometimes. Yes, it's good. It's good stuff. I'm sure it's not as good as yours, but we can follow the recipe like anybody else. All right, is everybody good with Is everybody good with that? Degree 2 extensions, quadratic extensions are actually square root extensions. Everybody okay with that? Yes. All right. So now, and then the situation for degree 3 and up is more complicated, as we shall see. All right. So now that we've sort of seen what happens with small degree extensions, let's talk about what happens with degrees of elements versus degrees of extensions, because remember we had this sort of review sentiment. Let me see if I find a less sickly green to talk about this in. So recall, degree of an element is the degree of its irreducible polynomial. And the degree of an extension is the dimension extension of f is the dimension of the extension over F as an F vector space. So remember, so we have these two ideas of degree floating around, and it's maybe not entirely obvious. I think it's not obvious that the two are related. The two are related, but fortunately they are, because otherwise that'd be a really terrible name to have if they were different. Okay, so right. So to say that F is algebraic, again, so if F is the theorem says that if if alpha is algebraic over F, then the degree of alpha is equal to the degree of F of alpha over F. Yeah, so the degree is equal to the degree, the sort of algebraic relation degree is equal to the dimensional degree. All right, so suppose that alpha is algebraic over F, then there exists some irreducible f of x in little f of x and big F bracket x, such that, and now let me switch over to pen, such that f of alpha equals 0. So yeah, so in that case, so once if alpha is algebraic over big F, then there's some polynomial. There's a unique irreducible polynomial in F bracket x, such that f of alpha equals 0. So then if the degree of f equals n, we know from before, so this is actually an old result, that that the set containing 1 alpha squared up through alpha to the n minus 1 is a basis for, I should say it's not just any basis, it's an F basis, is an F basis for F of alpha, F adjoint alpha, which is the same thing as F adjoint alpha as a ring. Right, so this is a kind of a neat property of algebraic field extensions. For algebraic field extensions, all these very careful distinctions that one might make are all blurred together. The sort of ring extension by alpha is the same, exactly equal to the field extension by alpha, and it has this tidy basis, and so this has, and this is oops. Let me actually put in another thing, something in a different color here. So this is a basis with n elements, basis with n elements in it. Oops. Yeah, it's a basis with n things in this, numbered 0 to n minus 1. So actually, I guess so the dimension of f of alpha over f is n by definition, because there's one basis with n things in it. Yeah, that's it. So it's not too complicated a thing, but it's important. So let me actually also recall something. Ask you to recall something, a related thing. So you may vaguely remember that I think we talked very briefly about how to compute in a finite field. So remember we had this idea that if alpha to the n plus, say, alpha sub n minus 1, alpha to the n minus, maybe, I hope we did this. Maybe I'm just remembering this wrong, plus alpha 1 is a1 alpha plus a0 equals 0. Then does anyone remember we talked about so what we do, the way that you compute, so the way that you compute inside the field f of alpha is that you use the fact that alpha to the n is equal to a sub minus a sub n minus 1 alpha to the n minus 1. So you put everything over on the other side, minus dot 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 minus a sub 0. So yeah, so when we do computations and say in some finite field, as we shall see, the way that so one way to sort of relatively straightforward way to do computations is that you use the defining the minimal polynomial of alpha to as a computational recipe that sort of allows you to express any larger degree polynomial as rewrite any larger degree polynomial, any polynomial with terms of degree greater than or equal to n, in terms of in smaller degree terms. And so by doing that over and over, you can reduce anything to a degree strictly less than n, and then that's how you compute in f of alpha. That wasn't so tidy. My bad. Anyway, does that sound familiar? Did I actually remember to do that in here, or did I do that somewhere else, or maybe I just did that in a previous? Who remembers that talking about that using the sort of the polynomial that has alpha as a root to rewrite polynomials in alpha? No is a perfectly acceptable answer. So chat box, who remembers that? Yes or no? No one remembers it. Okay. So let me. Perhaps I just did that somewhere else. Okay. So now let's see if I. This is a dangerous thing. Did I do it? No, I did that. I did it wrong. Okay. So it'll insert before. So let me go here, and then I'm going to insert a page. There. Okay. So instead of saying recall, I'm going to say note. I'm going to rewrite it again and make it look a little nicer. If alpha to the n plus alpha a sub n minus 1 alpha to the n minus 1 summed up all the way down to a1 alpha plus a sub 0 equals 0. So this is that means that alpha to the n is equal to minus a sub n minus 1 alpha to the n minus 1 minus, so you put everything over on the other side, a1 alpha minus a sub 0. Then that's true. And so what happens is that we can use this relation to compute inside the field f of alpha in sort of two steps. And here, let me go to typing to make this a little faster. Step 1, do all your computations in terms of polynomials. Computations in terms of polynomials in alpha. And then 2, you can use the above relation to reduce any term of degree greater than or equal to n to terms of smaller degree to reduce. So we end up with a polynomial of degree strictly less than n, which is a unique expression for an element of f of alpha, since let me switch to pen, since the set containing 1 alpha all the way up to alpha to the n minus 1, since that is a base is linearly independent, is f linearly independent. Yeah, I think we did do this, but I think I didn't make a big. Well, I probably didn't make such a big deal out of it at the time, and then I'm sure it wasn't apparent that this would somehow be useful or important. But at least, does that make sense now? So again, again to repeat. So if you have some f such that f of alpha equals 0, then you put everything, you put all the sort of lower terms on the other side, and that gives you a reduction algorithm for computing in f of alpha. And that's something we will use. Well, we'll use that. So does that make sense? Yes, no? Questions? Okay, and I think, yeah, we'll see some. I think so. I think this is most commonly used. You know, I think I got all the way through this course without it. I think without yeah. When I took this course, I think I didn't use this so much. But where this actually turns out to be really helpful is in terms of finite fields. And so when we do when we take a little stopover in finite fields, you'll see that this is sort of this is how you actually compute finite fields. Well, at least first in practice. I mean, in practice, in a finite field, what you do is you write down lookup tables, and those are very fast. But the way you make the lookup tables is to use this kind of computational algorithm. Okay, so let's get to the main event for today. So the main result of today is that degrees are multiplicative. Hooray! Suppose k is an extension of f and L is an extension of k. Then the degree of L over f is equal to the degree of L over k times the degree of k over f. And remember, the degree of L over f is the dimension of L as an f vector space. The degree of L over k is the dimension of L as a k vector space. And the degree of k over f is the dimension of k as an f vector space. Yeah, so remember, that's the definition of those three numbers. Right. Okay. Oh, here we go. Here's a sort of little pop quiz. Right. So let beta 1 through beta n be a basis for L as a k vector space. And so pop quiz, just from the review of what we were just doing. N. So which degree does that tell you is equal to n? Somebody want to take a crack at it in the chat? Great, L over k. So n is the degree of L over k, because the degree of L over k is the dimension of L as a k vector space. Great. Fantastic. All right, so next, So in a similar way, so if alpha 1 through alpha s is a basis for k as an F vector space, that so which degree turns out to be equal to s? Thank you, Trent. That's Trenton and Ruth. That means that s is equal to the degree of k over f. All right. So yeah. So we want that right hand side here. Oops. So that right hand side here is now this right hand side over here. We now this is n and this is s, and so we want to find a basis for L as an F vector space that has n times s vectors in it. So we're gonna so in the time-honored mathematical manner, we're gonna write down the answer and check that it's the answer. So it will be enough to show that the set containing I hope you maybe kind of guessed this. The set containing all the products of alphas and betas is a basis for the biggest extension L as an F vector space. So there's two parts of this, and I'll just briefly, and I mean, so the full details. Well, let's see how this goes. Let me start by sort of briefly indicating, and then if you want more details, I'll expand that. I'll add another page and expand that. So in order to show that we get a basis, we need spanning and we need linear dependence. So spanning. So if I guess we should. Well, if gamma. Actually, let me switch to pen. So if gamma is in L, then gamma. So we know that that beta 1 through beta n span L as a k vector space, and so gamma is going to be the sum of some beta j's with coefficients b sub j, where b sub j, each of these b's are in k, but then each of those b's is in turn, because so why is that possible? Because that's true because the betas are span, because the beta sub j's span L. But now each of these b sub j's itself is an element of k, and so and because the alphas span k, we see that each of those, each of those alpha, each of those b sub j's is equal to some a sub I j's, each of those b sub j's is equal to the sum of some a sub ij alpha sub i's where each of those a sub ij's are in F. And that happens because the alphas, so i's, span k. Yeah, and so this is like some sort of double sum of some a sub ij alpha sub I beta sub j. Okay, so now, does that make sense that the alpha betas span L? So, are there any questions about the spanning part? Okay. Oops. Sorry, that's my laptop does that sometimes. Okay, now linear independence is not dissimilar. Well, because we sort of start at the where we ended off. If we have that, we have a double sum of. So if we have some linear combination of alpha betas that's equal to 0, then what happens is because the beta sub j are linearly independent, we have that the sum, each of these sums, the sum of alpha sub ij, a sub ij alpha I is equal to 0, and then sort of a tidy little argument because each of the alphas sub i's, because the set of alpha sub i's are linearly independent. We have that all of the a sub ij's are also equal to 0. And there it is. That's a definition of linear independence. We start off with an arbitrary linear combination of alpha betas, and then we end up with all the coefficients being 0. Hooray! Yay! Linear algebra. So does that make sense? There's the linear independence argument. So everybody good with the basis, the whole basis argument there? Any questions about that? Anybody want to scroll up and take a look at the span part again? There's the span part. Anyway, I think on a personal note, I would say that when I was your age, when I was in college, I think I didn't really actually absorb as much of linear algebra as I should have. And now, but after having taught it a bunch of times, I really start to appreciate the elegance of those definitions, where you have the idea of spanning and linear independence, and how those definitions combine to make the idea of a basis. It's good stuff. All right. Anyway, so degrees multiply. Okay. I think let's move on to using multiplying degrees, and this is something more that we use all the time. All right. So we have the finite, the following list of following interesting consequences of multiplicativity. So if you have a finite extension of degree n, and you have an element of that extension, then alpha must be algebraic over capital F, and its degree must divide n. So that's statement 1. Statement 2 says that it's supposed to have a f prime is an extension of f, and L is an extension of f prime. So if you have an element of L that's algebraic over f, then alpha is algebraic over f prime over the bigger field. So if you have something algebraic over a smaller field, it must also be algebraic over a bigger field. And so, and we know that its degree over capital F is greater than or equal to its degree over f prime. So which means that that adjoining finitely many, which implies that adjoining finitely many algebraic elements will gives a finite extension, and then which then implies that the elements of K that are algebraic over F form a subfield of any field extension, including possibly infinite field extension. And I guess let me say that so the 2 and 4 don't use the multiplicativity of degree quite so directly. 1 and 3 definitely do. Instead of 16 minutes, and so instead of hemming and hawing, let me just go ahead and prove 1, and then sort of go on from there. Let's see how that goes. So here's a proof of 1. Well, what we have here is the thing to consider is, it's sort of helpful to draw these little diagrams. So there's this thing called a tower of field extensions. This is something we got. That's helpful to get used to. And so one of the main techniques that we have for working with field extensions is that you draw one of these diagrams of a tower of field extensions, and then apply multiplicativity of degree. So we see here, if we happen to consider the field extension f of alpha, then f of alpha is a field extension between well, not necessarily strictly, but between K and F. And so as soon as we have one of these chains of field extensions, one of these towers of field extensions, then we can apply multiplicativity, and we see that n, which is the degree of K over F, is equal to the degree of K over F of alpha times the degree of F of alpha over F, and this latter term here is exactly equal to the degree of alpha. So remember, that was a result we established earlier, that that the degree of an element is equal to the degree of its associated field extension. So there we go. Degree of alpha must be finite, and it divides the degree of K over F. It divides n. So that's cool. That's sort of not obvious. Yeah, that's not sort of not obvious. It's definitely not obvious. Especially when you have this slightly different result in number 2. So, so does that make sense? The proof of 1, and sort of how multiplicativity shows up there. Okay. 2, I think 2 is sort of is really sort of a lemma for 3, but let me sort of talk about how that works. So here, what happens here is that yeah, let me sort of draw the proof of 2. Actually, the diagram is sort of more interesting in many ways than the result. And so here's the diagram. So we start off with F, and we have a field extension F prime of F prime of F, and so so then we have F of alpha is an extension of F, and then f prime of alpha as an extension of f prime, and f. So we get this kind of diagram here, and all these things are contained in L. Oops, I kind of blended those in here. So let me draw a little dividing line. There we go. So does everybody see the diagram for this situation, where f is contained in f prime is in L, and alpha in L is algebraic over f. So here we're not going to directly use multiplicativity. What we're going to use is the definition of degree. So here, if f of alpha equals 0 for and little f is irreducible in over f, irreducible over f, then f of alpha equals 0. Well, I just said that, I know, but and f is still a polynomial over f with coefficients in f prime. It's just not so that and then what happened, and then the reason why we get this thing where the degree over f is greater than or equal to the degree over f prime, but not necessarily divides. So the irreducible polynomial of alpha over f prime is an irreducible factor of f of x, is a factor of f of x over f prime. It is an irreducible that is irreducible over f prime. Sort of the which means so its degree is no larger. All right, so that's kind of a, let's see how long do we go here? Oh yeah. Okay, so yeah. All right. So and here actually these diagrams are very helpful to show sort of where these divisibility things occur. So there's not, so I hope you can sort of see that, because even though this side of this diamond is written as parallel to this side of the diamond, that doesn't mean that this side somehow divides this other side. It could be pretty different. Okay, right. So anyway, so yeah, if you're, so the point is, the point of 2 is that if you're algebraic over the smaller field, then you're algebraic over the bigger field. So let me actually sort of, I think, yeah. So let me just leverage that to prove number 3, and then we'll see how that goes. So 3 said, so let me type that over here. So this is proof of 3. It says adjoining finitely many algebraic elements to F gives a finite extension, which might seem natural until you think about it, and then all right, so that's what we wanted. So we want to show that adjoining finitely many algebraic elements to a field extension F, to sort of a base field F, gives a finite extension of F. So we know this is true for adding one element, since the degree of f of alpha over f equals the degree of alpha as an element. Yes, so the degree of the field extension is equal to the degree of the element. But after adding one element, so I guess let me put it this way. So what we really want to do is we're going to think proof goes by adding these algebraic elements that are algebraic over f1 at a time. Sorry. So we know that this is true for adding one element, since the degree of the extension obtained from one element is equal to the degree of alpha. But after adding one element, alpha sub 1, actually, after adding one element, we get, so what we get is you add, put it this way, alpha 1, and you get f of alpha 1, which is algebraic over f of finite degree. And then what happens is that from the previous lemma, previous result, then alpha 2 through alpha, let's say k, are all still algebraic over f of alpha 1. And so what happens is, so proceeding by induction, we add on the elements one at a time and get a finite extension each time by the multiplicativity of the degree. The full extension, the end result, still has finite degree and is therefore a finite extension. So that's another example of kind of thing that we can prove using multiplicativity of degree. We're not like in a huge hurry. I think actually just to do one more. Actually, let me see, Ravi. What you had a question about you had a question about what was it again? Can you open your mic and say what it was? And where did you find that question? I was wondering why, because it didn't look like something from homework.
It's from the Gallian book.
From Gallian, right. So, and you were asking, so Ravi had a question from Gallian. And do you remember how it goes?
The rational numbers adjoined with root 2 and root 3 are.
Oh, and you had it. Right. How to prove that? Because this actually turns out to also to be of This actually also turns out to be an application of multiplicativity, or this is one way to do it. Q adjoin two elements, root 2 and root 3, equals Q of root 2 plus root 3. So that you're asking about that from Gallian, right? Ravi, that's right?
Yes. Yeah.
Okay, so one good method for this particular problem, I think it really for this, maybe for even for this genre of problems, is to actually so one method, do set containment both ways and multiplicativity of degree. So let me draw the picture that goes with that. Yeah, so I thought this is a good question that kind of goes with what we're doing here. So we know, because on the one hand, it's relatively clear. Well, certainly Q of adjoin root 2 and root 3 contains Q adjoin just the sum of these things, right? So that works. And so then what we get is we get this tower, Q of root 2 and root 3. And we get in the middle, possibly, but Q of root 2 plus root 3. And then Q. All right, and then we sort of get the whole, actually, let me erase that. So we can sort of go about this in two different ways. So we could also get to from Q to Q adjoin root 2 and root 3 by adjoining root 2 first. So is everybody good with that so far? So you can use this tower, this sort of diagram of field extensions. Oh, okay. We're almost out of time. So and so what happens is this has degree 2 because it's an element of degree degree 2. Now it's not obvious that the degree of root 3 over root 2 is 2, but we certainly know that's at most 2. And then what you do is then you can show by direct computation. You can show by computation that this degree is equal to 4 because yeah, well, you just compute the irreducible polynomial of root 2 plus root 3, and so then this degree has to be 4, and so it follows that this degree over here must be 1, because the only way to get a 4 on one side and something on the other side, a 2 and something that's either 1 or 2 on the other side is if this degree is equal to 1. So that's at least a sketch of how to do that. So, Robbie, does that make sense? So this degree must be 1. Yeah. So yeah, why must that degree be 1? Because the right-hand path gives degree 2 or 4. Right? If you go up the right-hand side of this diagram and you multiply those degrees, you get degree either 2 or 4. Either this first degree is 2 and the second degree is either 1 or 2. So the product is either 2 or 4, and the left-hand path gives degree a multiple of 4. So the only way you can get something that's 2 or 4 on one side or in a multiple of 4 on the other is if they're equal to 4, and so that last degree must be 1. Make sense? Yeah. So I hope that was helpful for everybody, because that is actually a very good illustration of how to use, of how to use the multiplicativity of degree. Okay, we are out of time. We're 3 minutes over time. Sorry to go over time. And I guess next time we'll pick up with other consequences of multiplicativity. But maybe we'll just sort of go to find. I think that was probably enough consequences of multiplicativity. So we'll pick up next time. We'll start here on Monday. Okay, thanks everybody. Bye.
Thank you.